This is not work that done with Ted, but I think he would have liked the results and found it very interesting. So for many of you already know that if you don't know, the SAFOD project was and is drilling deep into the San Andreas Fault to study the fault properties at depth. And let me start by not talking about it. I'm going to bring in something else here just to, while I have the chance, just to emphasize the sort of the broad range of Ted's impact on work. And these concepts, really I wanted to emphasize this paper, which is a real gem of a paper in '83 on microcrack connectivity in rocks. And when I came here to work with Ted, it was mainly to look at resistivity processes in rocks, but my background had been in deformation and brittle fracture in rocks. And at the time, if you had asked me, well, what does permeability or resistivity in rock have to do with fracture, I said, well, they're really two very different things. But in Ted's world, they're probably more like two sides of the same coin. And this paper really shows in his sort of global way of looking at things, he really was able to synthesize different ideas. And in his notion, he recognized that on the small scale, this is a 2D representation of a fracture network in rocks, that at the grain size scale, that's where the action is happening, or the interaction of microcracks. But what you're interested mainly in is the sort of stepping back and looking at the properties of the rock ensemble as a whole. And the problem is, how do you deal with these very specific small grain size effects and then integrate them out to the overall properties? And that's where these concepts come in, that Ted's idea was that you can break down the system into very small components that you can solve easily. So you can understand the stress and strain distribution on this small network of cracks and solve that. And then you do this for each one of the elements and then get an average property of either grouping these in groups of 2 by 2, or in this case 3 by 3 elements, and get a property of this overall matrix. And that's the sort of the renormalization group concept. And then that gives you this element in the sample, and then you take another group of 3 and get the larger properties by grouping again until you work up in scale to the overall average properties of the material. And it turns out this becomes a very efficient system for solving the numerical problem. My main contribution in this study was to say that, well, for brittle failure, you need diagonal cracks to represent the shear failure in the samples. The simplest thing is just to have vertical and horizontal cracks, which works okay for the, transport properties. And I think probably Eve is going to talk more about this later on. But if you want to look at the brittle fracture, I think it works much better if you also allow for shearing type failure. So if you carry this process through, and I coded this up and made synthetic deformation experiments on 2D granite samples, you get a suite of runs, for example, like this, which is stress-strain plots, showing that as you increase confining pressure, you get this very characteristic increase in strength, which if you then come over and do a shear normal stress plot, you get a failure envelope that looks like this. It's curved. And if you compare it to real data, here is laboratory data from Jim Byerly back in the 60s of deformation of granite and a failure envelope, and you find out that you get a very satisfying result from this very simple conceptual model that really is Ted's idea. And you can look at the crack densities that go on. Here would be a starting crack density, sort of random distribution of cracks in the starting model. And as you load it up, you get, it doesn't show up very well here, but you get concentrations of new cracks showing up here and a lobe here where it's localized the fracture damage, and down here. And I've just emphasized that with this dashed line showing an incipient failure surface that's developing in this synthetic sample or numerical sample. And for comparison, here would be a real granite sample where each dot is acoustic emission from a source of a microcrack in the sample. And early on, you see very distributed deformation in the sample. But as you get to peak stress, then this suddenly localizes into an incipient fracture plane that then grows, and very, very reminiscent between the numerical modeling and the real experiments, real world experiments. So this whole approach, this is one aspect. I could talk a lot more about how this plays out if you add time-dependent processes as well. And I think Ted and I learned a great deal about brittle fracture in rock from these exercises. Okay, so I just wanted to point that out in passing. And now back to the San Andreas Fault. So I just have to give a little background in case people aren't familiar with this. The SAFOD project happened here in the central California, where the red marks the brittle part of the San Andreas that, for example, this is a 1906 breakage of the rupture zone for the 1906 earthquake, and the 1857 earthquake went south in the southern part of the San Andreas, and in the blue is the creeping section, and SAFOD is just in the transition within the creeping section of the San Andreas Fault, just close to where it's locked going south. The idea, it was to drill down deep vertically and then side kick and cross the fault at depth and retrieve core and do geophysical measurements of the San Andreas at depth. And I'd like to show this picture. This is a picture probably 15 years old. These are the sorts of iconic pictures that were always shown of the SAFOD project before the fault or before the drill hole was actually in place. And they're always done in the background. There's a drill hole, but in the background it's overlaid on a picture of the resistivity. And Ted, of course, knew that fault zones are low resistivity zones, and a massive fault such as the San Andreas that has deep roots will actually provide a conductive path for current to flow from the upper crust through to the mantle, and so you can really light this up. I think Randy spent some time working on these issues of because there's current flow through the fault zone to the mantle, you can actually get the structure of properties of the fault zone from MT studies. In any case, this is sort of a given that the fault zone shows up as a low resistivity zone in these sorts of studies. So for the SAFOD fault, again, the idea was to drill vertically down to get some depth and then cross the fault at some depth here, do rapid drilling, and this was phase one done down to here, and then in 2005, phase two was rapid drilling actually across the fault zone. In reality, it was actually crossing the fault at a vertical depth of about 2.7 kilometers, not as shown in this diagram. But then phase three happened 2 years later. Sidekick multi-drilling core to obtain core from the crossings of the fault zone in the third part of the drilling process, and I'll be showing resistivity results from core that were taken in this sidetrack drilling. So here's a map view to orient you to the geometry. Here we've rotated the picture so that the strike of the San Andreas Fault is vertical here, and this is one boundary of the fault zone. It was found from the wireline logging primarily, and also from spot core or from cuttings that were taken during phase two drilling in 2005, which cuts across the fault like this. that the damage zone is about 200 meters wide at this location. Again, it's at about 2.7 kilometers depth. And there were two places where casing deformation was observed in the casing of the phase 2 hole here and here that showed where the fault was actively creeping. And this zone in orange is referred to as a central deforming zone, and this is a southwest deforming zone, or CDZ and SDZ. So then 2 years later, the coring operation was done. This red curve, it was a multilateral core drilling, and cores were taken, a total of 2 places. Cores were taken to target where the creeping sections of the fault were identified in the phase 2 drilling. So this yellow section is one set of core, and then the second to find the central deforming zone is this section here. A total of about 30 meters of core were recovered in the process. And this is what the core looks like. It was studied on site. Some basic measurements were made, and then it was transported to the IODP repository at College Station, Texas. So this is a section of the core. It's wrapped in plastic to keep water in the core so it wouldn't dry out, and put in cold storage to preserve it as well as possible. So here, in one of the times that I went to sample, we've sliced up the core, and the better parts of the core, you can make decent slices like this of it. Other parts of the core, especially the more bands that are deforming more, are very crumbly, and it's very difficult material to work with, but we did our best, and you can end up with samples like this that would be a sample that we would test resistivity and permeability on. So these would be undisturbed or whole, or undisturbed core samples. It's a real challenge to work with some of these fault zone materials. So here's the setup that we used for the joint permeability resistivity measurements. The sample would be here in a pressure vessel. It's jacketed with steel end plugs and porous sandstone wafers on either end of it. For the permeability measurements, we would have a pump providing upstream pore pressure that would flow through the sample, and then high pressure tubing bringing it back out of the pressure vessel to atmospheric pressure. To do the resistivity at the same time, the lower half of the sample assembly had to be insulated electrically, so we had to make a special setup that would bring high pressure tubing out through the end plug here with an insulator, so that we could apply here, in this case, a 2 kilohertz sine wave through a decade resistor box in series with the one end of the sample. The other end of the sample is grounded. So all you do, you apply the voltage of the signal to it, and you just adjust the decade box so that the voltage at this point is half of the supply signal, and then you can just read off the resistivity of the sample from the decade box, resistor box. We use fluid that, one of the problems at SAFOT is it was very difficult to obtain fluid samples of the pore fluids in the formation. So we don't have fluids directly from the deformation zones farther down into the Great Valley sequence. We do have fluids, and that's what we matched in our as a pore fluid that we used in our conductivity measurements. And this actually becomes an issue later on in matching the wireline logging data to the core data. But here's what the results look like. We were able to sample 17 pieces of core spanning the whole range of representative rock types in the cores. And here we're plotting effective confining pressure on the horizontal axis and resistivity, log resistivity on the vertical axis, and you typically get these, these plots where as you apply more confining pressure to the sample, you squeeze down this pore space, and so the resistivity goes up. So we get these sloping curves for each sample. And one thing that you notice is that the foliated gouge, which is from the actively creeping sections, is always the lowest resistivity in the rock types that we measured. So just to plot these results up, we're going to take values at 100 megapascal effective pressure and then at 40 megapascals effective pressure. The 100 megapascals would be roughly equivalent to the pressure that you would get for hydrostatic pore pressure in the pore space. We don't know what the pore pressure is in the formations crossing the fault, so there is some speculation that it may be overpressured, in which case values down here might be more appropriate.
What's the difference between the different wire sum, like a ohm meter, and there's 1,000? What's the difference between these rocks, or what are they?
Each one of these is a sample that, well, if I show this slide, so here now is the measured depth in the phase 3 drilling. So like the SDZ, for example, the foliated deformation zone would be at this depth range. And here is a sort of host rock, the rock right around this, and the surrounding rock here in the CDZ. These are all damage zone rocks. So each of these samples is a different one of these rock types, either from the damage zone out here or from the foliated gouge, which is the deforming zone here. So here we have profiles. The upper curves here are for the coefficient of friction that we measured separately on these rocks. And what you find in the host rock, here we have relatively high coefficient of friction. You get into the actively deforming zone, and the friction drops way down to about 0.1 to 0.15. This is because there's high clay content in here. And then we come out the other side. So this is damage zone rock now, but not actively deforming, and the strength recovers. In the central deforming zone, again, we have very low strength here and somewhat higher strength outside of the actively deforming zone. So for comparison, here now is the resistivity plot that I showed from the data in the previous slide. And we see in the host rock, we have relatively high resistivities, about 1,000 ohm meters. But we get into the actively deforming zone, and it drops down by 1 to 2 orders of magnitude in resistivity, and then recovers in the damage zone to the right here. And then for the central deforming zone, again, the lowest resistivities are within the faults, within the actively deforming clay-rich layers. The low resistivity is probably due to the fact that these are clay-rich materials that are deforming. And on either side in the damage zone, we have about a factor of 10 higher resistivity. Okay, so I'm going to jump for a moment here to the wireline logs. This is from the Zobak et al. Paper, EOS paper that described the results from the wireline, from the drilling operation and phase 2 drilling mainly. So again, this is a profile of measured depth in the phase 2 hole. And at the top, you have resistivity and then shear and P-wave velocities and the rock density here. And what you can just barely see, well, first the pink or reddish lines here are the SDZ and the CDZ zones that I just have described before. And you see a big drop in resistivity that they measure in the wireline logging here in the SDZ, and another large drop in the CDZ. So the resistivity, again, on this scale is very indicative of describing the structures within the actively deforming zones in the San Andreas. between the velocities and the resistivity, these are mainly how they identified where the damage zone was, spanning this region. And then later on, they looked at the deformation of the steel casing in the hole, and that was how this, for example, shows the deformation here where the major deformation was occurring in the CDZ, and then a very small deformation signature identifying the SDZ here. Okay, so I'm just going to wrap up by showing a comparison of these two. These plots on the bottom are what I showed 2 slides ago for the core resistivity measurements. But up here, these are kind of busy slides, but this is from the wireline logs. And the things to focus on are the dashed blue and green are the P and S wave signatures. Again, here's the SDZ showing up here, and there's a drop in resistivity, or in velocities there. And in CDZ, you also see a drop in the velocities. The solid black curve here is the 10-foot resistivity log. This is measuring from transducers 10 feet apart in the borehole. And we see, again, this high resistivity coming into the SDZ, and then a massive drop in resistivity and recovering on the northeast side in the damage zone. And again, around the CDZ, again, another drop, essentially mapping the high clay content actively deforming zones. So again, these line up very nicely with the shapes of the resistivity that we get from the core data in both relative resistivity and the drop in resistivity in the actual deforming zones. There is a vertical offset. These are something like a factor of 10 higher resistivity than what is observed in the wireline data, but there are a couple of reasons that this could be. One is there may be contamination here of drilling fluids, which are highly conductive, contributing to the overall resistivity measurements in the wireline logs, or we may have the wrong brine resistivity of our pore fluids from that we're using in our tests of the core samples. But the general structure of this is a very good agreement between the two.
1 minute.
Okay, I'll just wrap up then. That's perfect. So in general, the wireline resistivity and the core sample show good agreement. The fluid chemistry, which is still one of the highest priority items to do in the future, is to get fluid samples from the actively deforming zones at SAFOD. And this will help us resolve some of the discrepancies between the absolute magnitude of the wireline and core resistivities. The actively deforming zones show up very distinctly as low resistivity, mainly due to high clay content. And this is something that people are finding throughout, in pretty much all of the deep scientific drilling operations that are crossing active fault zones. That in the shallow crust, the faults generally are characterized by having high alteration clay content in them. So the damage zone, again, has reduced resistivity. And I think I will end there. This is work, the resistivity work that we've done. As far as I know, we are the only group that has done this on SAFOD core. And it wouldn't have been done if I hadn't been interacting with Ted and understanding what the importance of this is. So I'll just bring that back. And one other thing, if you notice, 3 of the 4 co-authors on this work are all MIT people. There's a real synergy here that Steve Hickman, Carolyn Morrow, myself, we all have had a major impact from being associated here at MIT. So thank you.